So we're going to talk about electronic structure today, and it's important that we remember that as we left GCSE, this was our understanding of the atom. This is the kind of Bohr model, I suppose, for want of a better phrase. We've got 11 positive protons in the nucleus, and then we've got 11 electrons, and each of those has a negative charge. And in the first shell, we can have 2 electrons, and the second shell we can fit 8, and in the next shell we were also fitting 8. And in this case we've got sodium, and you would have written the electron configuration of sodium as 2, 8, 1. That's where we were. That's where we started from. Today we're kind of going to admit that there's a much more complicated structure that sits underneath this. Some of the rules that we've got here are going to stay, and they're not going to change. Other rules, they're going to be amended slightly, and a lot of them are going to be significantly changed. Okay, so strap in, pay attention. We've got lots of practice questions coming up, and let's see how we go. So here's the A-level periodic table. Now the periodic table isn't particularly different from when it was at GCSE. We have the periods on the side, so we've got 1, 2, 3, 4, 5, 6, and 7, and these tell us the number of shells or energy levels. I'm going to use the word shells, but you could use the word energy levels. That would be completely fine. And then you've got your group numbers at the top, and you've got 1, 2, 3, 4, 5, 6, 7, and 0, and the number of electrons in the outside shell. So the outer electrons are here. We need to remember that one is 8. That's all pretty straightforward. And if we wanted to find out the electron configuration when we were at GCSE of an element, let's say we wanted to find out the electron configuration of beryllium, there are a number of ways we could have done that. We could have looked at the atomic number and seen it has 4 electrons, and then just put 2 in the first shell and 2 in the second shell. Or we could have checked that by saying it's in group 2, period 2, so it has 2 outer electrons in its second shell, and we'd know we were right. And these kind of ideas are still going to be things we draw on. Yeah, the number of principal shells or energy levels is still the number of periods. The number of outer electrons is still going to be really, really useful to us. But do you see that in an A-level periodic table, very specifically, they have numbered the transition metals. So now these brackets go all the way up to 18, and that's going to be crucial for us. Okay, so now when we're counting across, we will also be using the transition metals. That's a key change that's going to happen. So when you're doing this practice and you've got a periodic table in front of you, make sure you've got it labeled up so you know which rules are still in fact true and which rules are a little bit adjusted. Now, the idea of the change from the Bohr model to the current model of understanding of electron configuration all comes from this idea of ionization energies. And so what we do is we take an element, I'm going to use the symbol M, and we make sure it's a gas because we want to make sure it's a fair comparison, so we want every element to be in the same state, and it's a lot easier to do these experiments at higher temperatures, high energy situations, and try and cool liquid nitrogen down to its level to do it all at liquid phase or something like that. So we're going to make everything a gas, and what we're going to do is we're going to put in energy, and what we're going to do is we're going to get one of those outer electrons in our atom, and we're going to put in so much energy that that outer electron gains enough energy to escape. We're going to ionize it. Okay, so we're going to be left with an M that is a positive ion, and it's still a gas, and an electron. And if you look at this and you think that's really, really similar to what we did in the mass spectrometer, then you'd be correct. This is the exact same process, but instead of using a kind of mechanical process of physical collision, we are using an energetic process where we're kind of putting energy into the atom until the electrons gain so much energy that they get lost. Now we say that this is the first ionization energy. And the reason we say that is because it's the first electron that we're moving. So the outermost electron is being lost here. So we start with the outermost electron and we can lose successive electrons. And we can define this as the energy needed for 1 mole of gaseous atoms to lose 1 mole of electrons. Now, electrons can't be gaseous, so we don't have to worry about it there. And also we can rephrase this the other way. We can talk about losing 1 mole of electrons from 1 mole of gaseous atoms. It doesn't make any difference. As long as we've got this idea that we've got 1 mole in it in both cases and we've got gaseous in it, we're going to be fine. Now, if we take the second electron and we want to remove that, then we're going to start off with M+, and we're going to go to M, that's a gas, 2+, and an electron. The first ionization energy has already happened. Notice there's a +1 overall charge on the left, and there's a +1 overall charge on the right. We're just talking about the second step, not the first and second step together. So how does that change our definition? Well, the second ionization energy, let me get my right colored pen back, sorry, is the energy needed for 1 mole of gases, but they're not atoms anymore, they're +1 ions to lose 1 mole of electron. And the third ionization energy would be +2 ions, and the fourth +3 ions, and so on and so on and so on, until the element in question has lost all its electrons and it's just a tiny, highly positively charged nucleus floating in space. So these definitions are kind of sequential in their origin, but the most important thing I want you to remember with these ionization energies is they're each individual steps. So the first ionization energy is just the energy to remove the outermost electron. Then the second ionization energy is just the energy needed to move that second outermost electron. And this is really important because it tells us lots of information about the structure of the atom. And we call these successive ionization energies. Successive, one after another. So in this section we've talked about what an ionization energy is, how the different ionization energies can be recorded. We talked about the need for it to be a gaseous atom or ion, and the idea that they happen one after each other. Now it's time for you to have a little bit of practice to check you've understood. So here's 4 quick questions. Pause the video, write out the equations, unpause it when you're ready, and I'll show you the answers in a second. Good luck. Okay, let's check these answers quickly. Here they are. Just zoom out slightly to make sure we've got that on the whole page. So make sure you've always got a gaseous. It gets a bit boring, but it needs to be there. Make sure you've always got 1 electron being lost at each stage. Don't lose 3 electrons. Okay, they're really important. So when we look at this data, it tells us something really, really important. Because not each element has the same successive ionization energy. So what I'm going to do now is I'm going to show you the successive ionization energies of sodium. So here's a graph that shows you the successive ionization energies of sodium, and here's a model of the Bohr structure of sodium that we kind of are really, really familiar with. And what I want to do is kind of put these two together. First of all, in sodium, obviously it's famous for having its 1 electron in the outer shell. Okay, and on this scale, okay, the first electron is down here, and it's really, really easy to remove. Now, if we remember some of our understanding about group 1, that's not a surprise. Group 1 metals are highly reactive because they find it very easy to lose their outermost electron. So in this case, that one is really easy to move. Now when we get to this stage here, where we're in the 2, 3, 4, 5, 6, 7, 8, 9, you can see that there's a little bit of a jump at the beginning. This line here is steeper, and then there's kind of a gradual increase. And this is us, so we've already removed the first electron there. This is us removing these 8 electrons from this second shell. So as we do that, it gets progressively harder. Now, the jump that occurs here is all to do with a change in a thing called shielding. Now, shielding happens due to the nature of the attractive forces between the nucleus and the electron. So in my nucleus I have a positive charge, my electron is here, and there are attractive forces because opposite charges attract. If I was to put an extra row of electrons in here, so here's my ring of electrons here, here's my shell, here's my shell of electrons around there, then this electron is going to repel that electron away. There is a repulsive force here. There's a push that way, okay, and there's a push that way. They are counteracting each other. That means the attractive force here and here that's pulling this electron in is becoming less. So as shielding increases, the ability to lose the electron from the outside shell gets easier. In this case, what's happening here is this first jump here is to do with shielding going down, because we've gone from the outer ring of our sodium atom to the one inside it. Now there's one less ring of electrons, one less shell of electrons there to repel, so that means there is a jump in the first and the ionization energy, the successive ionization energy. So between the first and the second, there is a jump, because we go from outer shell to the second shell. This increase here, this is to do with something completely different. In this case, we need to talk not about the shielding, because they're all the second shell. So this one's gone. When this one's gone, this atom now has 11 protons and 10 electrons. So overall it has a charge of +1. When I take away the second electron, this number drops to 9. So now it's a +2. And what that does is that causes the nucleus to pull more strongly on the remaining electrons. So they have a slightly stronger hold. Same amount of protons haven't changed, it's still sodium, but there's less electrons, so the electrons are held more tightly. And the atom will get slightly smaller, its atomic or ionic radius will reduce, and then if we lose the next one, we've got only 8 electrons now, and we've got a charge of +3. So as this line goes up, what's happening here is we have less electrons and we've got a stronger pull from the nucleus. So that's causing this. Now the whole time I've been talking about this, you've probably been spending most of your time focused all the way over here on this massive jump over here. Now this massive jump occurs when we get to the situation where we've lost the first shell of electrons and the second shell of electrons. This jump is the removal of this second to last electron. And because it's so close to the nucleus, there's a really, really strong attraction in here. Okay, so we get this huge jump. This tells us that the shells must be a thing. We have a jump here, and we have a jump here. Now this jump's smaller than that jump, but they're both bigger jumps than we see in the 8 here. We have a 1, we have an 8, and we have a 2. Now we said our electron configuration for sodium was 2, 8, 1, and these are our shells. And you can see that the data supports the existence of these shells. Instead of looking at the successive ionization energies, we can also look at the first ionization energy for each element within a period. So this is period 3 elements. You've got sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. And although we can see that there is a general trend, that is an increase, it's got some oddities that occur between it. We've got an increase, then it decreases, then we've got 2 increases, then it slightly decreases, and then we've got 2 more increases. And this tells us extra information. Our current Bohr model of the electron configuration does not fit this. The general trend is quite easy to explain. In the general trend, as we go along the period, the number of protons in the nucleus increases. We say the nuclear charge increases. But as we go along the period, if we remember from our periodic table, everything in the 3rd period has 3 shells. So our shielding, that is going to stay the same. That is not changing. So if nuclear charge is increasing, but shielding is staying the same, then the attraction between the electrons and the nucleus is going to increase, and therefore the first ionization energy is going to go up. So explaining the general trend is quite easy, but explaining these dips becomes very confusing if the model that we use currently at GCSE is 100% accurate. And surprise, surprise, it's not. So what I've got for you here is some questions to help you think about what we've just talked about. If you need to go back and rewatch the video, feel free to rewind, but pause the video here, have a go at these questions, and then in a second I'll move on and show you the answers. Okay, let's look at the answers. So again, pause the video, make sure you know how you've got them right or wrong, and what you need to do differently next time. When we get all these ideas and we put them together, we end up with a more advanced understanding of atomic structure. And so what we end up with is something called orbital theory. And what we have is we have our energy levels still, which you would maybe call shells. And so these lines here tell us the boundaries between the shells, these vertical lines. So this is the first shell, this is the second shell, and this is the 3rd shell, and this is the 4th shell. And these shells are broken up into subshells. So in this case, the second shell is broken up into 2 subshells. And those subshells can be broken up into things called orbitals. And orbitals are shown by these boxes here, and these boxes are the orbitals. So the 3D subshell has 5 orbitals as an example. Each of these orbitals can hold 2 electrons, a pair of electrons. So if you look down here, we've got the first shell, as we would know it from GCSE, and the first shell can hold 2 electrons. And if we look at our diagram, we've got 1 box. So that box can hold 2 electrons. So the first shell holds 2 electrons, and orbital theory fits with what we know from GCSE. In the second shell, we're expecting the second shell to be able to hold 8 electrons. Now, if we look at the number of boxes, we've got two subshells here, the 2s and the 2p. We've got 4 orbitals in total, so we can go 1, 2, 3, 4, 5, 6, 7, 8. We've still got 8 electrons in the second shell. Now in the third shell, we would normally expect it to go up to 8 from GCSE. But the third shell has changed slightly. We now have this extra block here that's called the 3D subshell, and it has these 5 orbitals. So the third shell now holds 18 electrons. And this is to do with the transition metals, and by the end of this video you'll understand how this works. And then you've got the fourth shell, and it also has 4s, and it has this 4p subshell. It actually has other ones that go on, so it will have a 4d, and there's also a fourth type of shell that's known as the F. Now these letters aren't that important. They correspond to different shapes of orbitals. The orbitals themselves are kind of mathematical areas of probability where we expect to find electrons. All that information, the shapes of them, for example the S being spherical, is not required in your specification. I've put a picture up so you can see the shapes quickly, but just be clear that as long as you know the letters, you'll be perfectly capable of scoring full marks in any question to do with this. So we've got the S, the P, and the D, and kind of caveated, the F also exists. So some questions for you. Okay, these are just to make you think about these ideas. We're going to expand on these and have loads of practice in a minute. So if at the moment you're a little bit unsure, let's just see if we've got the basics in play. So pause the video, have a go at the questions, unpause, and in a second I'll show you the answers. Good luck. So here's our answers. Okay, check you've got them all right. It's important to remember that electrons can only exist in the shells, and therefore they can only exist in the orbitals. Now, this leads to something called S, P, and D blocks. So when we look at the periodic table, we see repeating patterns. That's the strength of it. And what we find out is because every period begins with the s orbitals first. So we've got 1s, 2s, and 3s. And these are the first 2 electrons in the period. The group 1 and group 2 elements are the s block. And if we look at period 2 has lithium and beryllium, and they are in the s block, so they're filling those first 2 s things. And then it continues over here with boron, and then it goes boron, carbon, nitrogen, and it ends in a total of 8 electrons because there are no transition metals nearby. So these elements here are the ones that fulfill the p orbitals. So we've got 1, 2, 3, 4, 5, 6 in a block here. We know that 6 electrons can fit in the p orbitals. So this is called the p block. So we would say that nitrogen is a p block element because its final electron, its outermost electron, is in the p block. We'd also say that bromine is a p block element because outermost electron is in the p block. And then the d block can hold 10. And when you see those 10, here you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 transition metals. And so the transition metal block is actually referred to as the D block because it is where the elements have their outermost electron in the D block. So if we're asked about S blocks, P blocks, and D blocks, what we do is we break it up like this: group 1 and 2, the alkali metals and the alkali earth metals, they are the S block. The block on the right hand side that contains all the non-metals and metalloids, that is the P block, and then the transition metals are called the D block. The final bit is down the bottom here, and we don't really cover these in much detail, but the radioactive elements that are in the lanthanides and actinides, they are technically in the F block. So if you ever want to know anything about them, we've just described them as being F block elements. The F block is not covered in our electron configuration required in our specification, apart from the fact that you need to know that it's called the F block. So we've actually got S block, P block, D block, and F block, and they fill in that order. Here's a simple question. All you've got to do is go down and say if each one has its outermost electron in the S, P, D or F, and so which block it's in. Shouldn't take long. Pause the video, off you go. And here are the answers. Make sure you've got them right. E is uranium, so it's in the F block. Very, very rarely you'll be asked about F block elements, but just so you know, that's where it is. So what are the rules for determining the electron configuration? We've got a number of rules. I'm going to go through each of them in turn, and I'll give you an example of how to do it. It's not a very nice colour. How to do it and how not to do it. There are basically 3 rules that determine everything. Okay? The first rule is known as the Aufbau principle. Okay? Aufbau is German. It basically means from within or from the center. And what they're basically saying to us is if we are filling our electrons, we fill from the center. Now the good news is you already know that from GCSE. You know that if you're filling an electron, you start at 1s. You don't randomly start at 3s. Okay, you know that already. That's pretty straightforward. The second rule we're going to talk about is we're going to talk about a thing called Pauli's exclusion principle. And what basically Pauli's exclusion principle says is that electrons can be paired. Now, you don't have to be able to recite these rules. You're not going to be examined on the rules, but these are their names, and this is how they're observed. But when we pair them, we have a thing called spin that we have to take into account. So, if we have an up and a down, we are happy. If we have 2 ups or 2 downs, we are not happy. So if I was doing this here and filling out the 1s, I would go up and down. I wouldn't go up and up. And our final rule is called Hund's rule. And it's technically Hund's rule of maximum multiplicity. People often call it the bus rule if you're stuck, because it works on the same logic as people getting on a bus. If you walk on a bus and there is an old lady sitting in the front seat and there's a space next to her, but behind her is a complete empty seat, most people would choose to sit on the empty seat and spread themselves out. Very few people willingly pair up with strangers because they want to observe that person's personal space. They want to make them feel comfortable. Okay, and electrons are the same. If we are going to fill the P block, for example, so let's say we're here, we've got a pair of electrons there, I've got a pair of electrons there, I fill these ones, the Aufbau principle, and I pair them, up, down, spin. But when I go here, if I put an electron here, I don't fill that box first, I make sure I fill these 3, and then I come back and I fill those ones. So I have 3 separate electrons first, like this, and then when I put my 4th electron in, I'm pairing them up. Okay, so that's really crucial. When I fill these electrons, they stay separate first, and they pair up. And this is because when they pair up, they're going to repel slightly. Okay? And this is a really, really important feature of these pairing, because it explains some of the data that we've learned. Now we've got those rules, we can put them into action. So what I'm going to do is go through the first, probably not 20 elements, actually probably the first 32 elements, actually. I think that would be better. Let's go through the first 32 elements. So hydrogen is really easy. Hydrogen, we have 1 electron in the outer shell. We say it has 1s1. It's got the 1s shell, or subshell, sorry, and it's got 1 electron in the outer shell. So we use the power to denote the number of electrons. When we go to helium, helium has a full shell, and it's the first shell that's full. So we pair that entire energy level first before we move on to the next one, and we change the denotation to 1s2. When we get into the second period, we've got lithium. Lithium is going to keep these 2 electrons, but it's also going to have a third electron, so that has to go in the next lowest one, the Aufbau principle, and we would say it has 2s1. So it's 1s2, 2s1. That's what we'd say. When we're going to beryllium, we have to pair here because this is a subshell. First of all, the 2s needs to be full before we can move up to the 2p, and again, we're talking about 2s2. Then our third goes into the p, 2p1. Our second doesn't pair because we have empty orbitals available, so 2p2 has 2 unpaired electrons, okay, Hund's rule, 2 separate seats in the bus have got 1 person each. And the same applies to the third one, which brings me to 1s2, 2s2, 2p3. Okay, now 2p3 is nitrogen. I've got 5 electrons in my second shell. So I'm in group 5, second period, nitrogen. When I go to oxygen, I pair this electron here. Okay, so now I've got 1 pair of electrons and 2 unpaired electrons. Then I pair the second one. Okay, so now I'm at fluorine, I'm at 2p5, and finally I get to neon, noble gas, 2p6, full outer shell, unreactive. 1s2, 2s2, 2p6. When I move up to the 3s, I've got 3s1, which is sodium. That's pretty straightforward. 3s2, which is magnesium. Again, no change here from the previous ones. Now in my periodic table, the next element in period 3 is aluminium. Aluminium is going to be 3p1. And then we have 3p2, 3p3, notice they're all unpaired, 3p4, 3p5, and 3p6. And that takes me to argon. So argon's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. And if you add all them up, 2, 4, 10, 18, argon is element number 18. It's got 18 protons. This is where the rules get a bit sticky. So when you go to potassium, which is element number 19, you'll see that it is in the 4th period and it's in the 1st group, which is part of the S group. So when I get to potassium, I need to make sure that I fill 4s1. Now right now, you're going to be looking at that thinking, but what about the 3D? Okay, but look at this diagram really carefully. We have followed a thing called the Aufbau principle, yeah, from within, from the lowest energy level up. We've been moving up the y-axis of this diagram as we've gone. And you'll notice that the 3D is actually slightly higher in energy. Okay, this is slightly higher than this. So that means the 4s fills and empties first. And that's the rule we need to remember. So here we have potassium, 3p6, 4s1. And then we have calcium, 3p6, 4s2. Now when we get to scandium, we're into the transition metals. And you remember I mentioned the transition metals are involved with this 3D. So you'll notice the 3D is slightly lower than the 4p, so that's now going to be the one that fills. We can think of this like a rising tide. Which bits is the coast going to hit first? It's going to hit 3D before it hits 4p. So now I'm back to green and I am 3D1. Now in exams, if you want to write 3D1, 4s2, if you want to write 4s2, 3D1, no one minds. As long as the numbers and the letters are accurate, it doesn't matter which order those two are in. Then we've got 3D2, which is titanium, vanadium, which is 3D3, then we've got chromium. Now chromium should be this, 3D4, 4s2. But you see how close these two are? See how close these two are? What happens is they're so close, and this is so close to being perfect, having everything balanced and full, that what happens is one of these electrons, instead of going into the 4s, it moves to the 3D. And so chromium is an exception. It is not 4s2, it is 4s1, it is not 3d4, it is 3d5. It is a special case. It's one of two that we're going to come across. So chromium is 4s1, 3d5. Now when we add our next electron, we're not going to be chromium anymore. We're going to come across to manganese, and manganese is going to repair, oh, got the spin the wrong way, repair these electrons, and it's going to change to 4s2, 3d5. 4s2, 3d5 now. So the 3d hasn't changed, we just paired up the 4s again. And then we're back to fill in the 3d orbitals. So we're going to go 3d6, now we're pairing, 3d7, where are we at? Cobalt, nickel, 3d8, and copper gets to 3d9. And copper is the other exception. Okay, so at the moment we think we are 3d9, 4s2, but again it's so close. So what it does is it pairs in the 3d and empties one from the 4s, and so copper is the other exception. It's 4s1, 3d10. And then finally we finish off with zinc. Zinc goes back to complete the pattern, and it's 4s2, 3d10. And then when we get to gallium and move along to germanium, we're back to our more familiar 3 there, so we go 4p1, 4p2, 4p3, and we're at arsenic, and then 4p4, 4p5, 4p6, and eventually we end up at good old krypton. So krypton is our last element we're going to talk about, and it's 1s2, 2s2, 2p6, 3s2, 3p6. These two can be in any order, 4s2, 3d10, 4p6, or you can go 3d10, 4s2, 4p6. And that's our electron configuration. Here I've got some practice questions for you. Pause the video, have a go at each one. It's going to take a little while, but promise you the practice is worth it. In a second, unpause the video and I'll show you the answers. Good luck. Okay, so here are the answers. How did you get on? Did you make sure that you got your blocks right? Did you make sure that you got your chromium right here? It's 3d5, 4s1. Okay, that's really, really important that you get those exceptions right. They like to ask you about the exceptions. Now we've practiced going from the element to the configuration. Now what we're going to practice is going from the configuration to the element. So pause the video. Which elements are these and which blocks do they live in? When you're ready, unpause and I'll show you the answers. So here we go. Here's all the answers and there's their blocks. How did you get on? Now, barium, if you didn't get barium right, I'd completely understand that one. It's probably a little bit unfair really to put that one in, but the rules apply exactly the same as all the other ones. You'll notice everything is the same. So if we put all this together, what does this tell us? Well, let's go back to this graph of the first ionization energies of period 3 elements. Okay, now period 3 has the same number of shells across the whole period. They will have 3 shells, or 3 energy levels. So that means our shielding is not a factor. Okay, our shielding has stayed the same. So we're not going to talk about shielding when we're trying to explain these dips that occur in the line. If we were going down a group, we could easily talk about shielding, because we know that as we go down a group, we increase the number of shells, so increase the shielding, making the outer electron easier to remove. But in this case, that's not going to be the issue. But our understanding of orbital theory can now explain these changes. So sodium has the outer electron as 3s1, and its first ionization energy is here. When we go to magnesium, we end up with 3s2. Now that is an increase in nuclear charge. Sodium has 11 protons, magnesium has 12. We've got an increase in nuclear charge, and we've got the same shielding, like we talked about the general trend. Aluminium drops. When aluminium drops, we have 3s2, 3p1. Now that p orbital is slightly higher energy. So here, this is higher energy. And because it's slightly higher energy, it's easier to lose that electron. That's what caused the drop. So although the nuclear charge has increased, it has got one more proton, this slightly higher energy is a bigger factor than the increase in the positive charge of the nucleus. And so that's what causes this drop. Now when we go to silicon, we've got 3s2, 3p2, and nuclear charge is winning here. And it causes a slight increase because this is the same distance as the previous one. And when you get to phosphorus, you end up with 3s2, 3p3. And so this trend is still nuclear charge being our big issue. When we get to sulfur, we get our other drop, and this is a less significant drop, but it's still a drop. This occurs because we now have 3s2, 3p4. So we have a pair now of electrons, and this means we have repulsion. And that means it's slightly easier to remove. And then when we go to chlorine, we've got 3s2, 3p5. This one has repulsion as well, but the nuclear charge is increasing, and still it's contributing to this general overall increase. And then we have argon, which is 3s2, 3p6. And again, the nuclear charge explains why that goes up. So when we're looking at increases like here and here and here, we're talking about nuclear charge being the overall factor. When we're looking at our two decreases that we've talked about, this one here and this one here, we've got two different reasons. One is we have a higher energy in the p block than the s block, which creates this difference, and the other is we have the repulsion from a paired electron at 3p4. So now we know enough about the orbital theory to explain the trends in successive ionization energies and also these trends across the period. So here I've got quite a few questions, and you may be thinking, why so many questions? Well, we've had quite a long video, lots of information to go through, and need lots of practice to understand what's going on. Okay, so pause the video, have a go at all these questions, then when you're finished, unpause it, and I'll show you the answers. So here's the answers. How did you get on? Pause the video. Remember 28 is over here, I've drawn them out. Okay, make sure you've got them correct. It's pretty tricky, but once you get the hang of it, it becomes quite easy. The key with this topic is to make sure you practice it regularly. so that you should be able to be given any element in the periodic table within the first 30, and be able to give the full electron configuration and explain any differences between the first ionization energies. Okay, if you've enjoyed the video, please make sure you like and subscribe, and leave a comment if you have any feedback for me. Thanks a lot. Good luck.